Have you ever been sitting on a high-speed train, just watching the world whiz by, and maybe wondered, beyond the big engines and the sleek shape, what actually keeps it all running so smoothly, so reliably?
It's a great question. There's this hidden world underneath, isn't there? These communication networks, like the train's nervous system, working constantly.
Exactly, the unsung heroes.
Yeah.
And that's what we're diving into today, the real complexities of two key players in train communication, MVB, that's multifunction vehicle bus, and the more familiar Ethernet.
Right. And our goal is to unpack how these systems affect what we call RAMS reliability, availability, and maintainability. How dependable is the train, really?
And we're going to look at this from two really important angles, which interestingly don't always point the same way.
That's the fascinating part. First up, there's service reliability and availability.
Okay, so this is about the train doing its job while it's running, like in service with passengers.
Precisely. Is it on time? Does it get from A to B without any function failing? Think no unexpected stops, that kind of thing.
Got it. And the second perspective.
That's asset availability.
Yeah.
This is broader. It's about the train being ready to go at all over the whole day. So this includes time at the depot, maintenance time, everything.
So it's more about the train's overall ready-to-roll status.
Exactly. Is it available when the operator needs it?
Right.
And looking at it this way can lead to some pretty different conclusions about MVB versus Ethernet.
Okay, this sounds like a puzzle. Let's start unpacking it. What are these two systems, MVB and Ethernet, in the context of a train? Let's start with MVB.
Okay, so MVB, multifunction vehicle bus, think of it as a specialized, heavy-duty internal communication line, mostly within a single train car.
Within one car, not between cars.
Primarily, yes. It's designed to connect the, let's say, the smart equipment, the programmable controllers, with the simpler stuff like sensors checking temperature or actuators opening doors, all within that one vehicle. It's not really its main job to talk between vehicles. But for what it does, it's very robust. Often you'll see redundant setups, two wires, or even optical fiber, just to make sure those critical signals get through within the car.
Like a really secure intercom just for one department.
That's a good way to put it.
Yeah.
And then there's Ethernet.
Which most of us probably know from like home internet or the office.
Exactly the same fundamental technology. But on a train, it's doing much more than just, passenger Wi-Fi, increasingly. It's connecting critical systems, too.
So it's more versatile.
Yeah, that's the big draw. It brings potential cost savings, more features. It uses the familiar twisted pair cables for end devices and often fiber optics for the main backbone running along the train.
So sticking with your analogy, if MVB is the secure intercom in one department,
Then Ethernet is more like the company-wide internet, connecting everything, computers, printers, security cameras, maybe even the phone system, all on one flexible network. It handles more data types, it's easier to expand.
Okay, that makes sense. So let's look at that first perspective again. The in-service performance. When the train's actually running, carrying people, what matters most then?
Well, we're focusing on critical functions, things like propulsion. The driver sends a command to accelerate, and that signal has to get to the motors reliably.
Right, that seems pretty important.
Definitely. Or display, making sure the driver sees the correct speed, warnings, all that vital info.
So how do engineers compare MVB and Ethernet for these jobs?
They use modeling techniques, basically creating computer models that simulate how these systems operate and, crucially, how often different parts might fail, assuming certain failure rates for comparison.
Okay, so they run the numbers, and what pops out? You'd think one network must be clearly better when things get critical, right?
You would think so. But here's the first, maybe surprising finding. When you look purely at the train in service, doing its job, the difference in reliability or availability caused by the network itself, MVB versus Ethernet, is actually, well, it's not significant.
Really? So for something like propulsion, it doesn't much matter which network is sending the signal.
The numbers bear that out. For example, the mean time to service failure, the MTTFS, for propulsion, including all the components involved, was calculated at around 34,600 hours for MVB.
Okay, that's a long time, almost 4 years running nonstop.
Exactly. And for Ethernet, it was around 35,947 hours. Very similar. The difference is negligible in practical terms for service delivery.
Wow. So if it's not the network causing the delays or failures during a trip, what is it then?
It really comes down to the end devices, the things connected to the network, like the traction control unit itself or the driver's display unit. Their reliability is what overwhelmingly dictates whether the train completes its mission without a hitch.
So the network's own contribution to, say, a train stopping unexpectedly is actually pretty small overall.
That's what the analysis suggests for in-service issues. If you want to boost that on-time performance, your main focus should be on making the controllers, the displays, the sensors themselves more reliable, rather than sweating the small differences between MVB and Ethernet network reliability during operation.
Okay, that's a really key insight for service reliability. But now let's pivot. What about that second perspective, asset availability? The train's overall readiness, including maintenance time.
Right. Now we zoom out. We're looking at the entire day, the entire life cycle, including time spent fixing things in the depot. Any failure that pulls the train out of service counts here.
And does the picture change?
Dramatically.
Mm-hmm.
Here, when we look at the reliability of the network components themselves, the mean time to failure of critical items, or MTTFCM Ethernet components, actually fail more often.
Wait, more often. How does that work if Ethernet is supposed to be better overall?
It seems counterintuitive, I know. The data showed Ethernet's MTTFCM at about 28,000 hours, whereas MVB components lasted much longer on average, around 120,000 hours.
Why is that?
A couple of reasons cited are the inherent reliability of Ethernet switches compared to MVB components, and also just the sheer number of switches you typically need in an Ethernet setup. More parts means more potential points of failure.
Okay, so Ethernet parts break more often. But you said it performs better for overall readiness. I'm missing a piece here.
You are, and it's the crucial piece: maintainability, diagnostics, and repair time. This is where Ethernet completely turns the tables.
Ah, okay. Tell me more.
While Ethernet components might fail a bit more frequently, fixing those failures is usually much faster, like incredibly faster. The average time to actively diagnose and fix an Ethernet problem, that's the mean active corrective maintenance time, or MACMT, is around 4 hours.
4 hours, that's it.
Yep. Think about finding the faulty switch or cable, replacing it, testing it, boom, back online in roughly half a shift.
And MVB.
That's the contrast. MVB, being more integrated and having, frankly, less sophisticated built-in diagnostics, is harder to troubleshoot. Finding the exact cause of a problem can take a long time. The average MACMT for any MVB failure was about 72.5 hours.
Whoa, okay, 4 hours versus 72.5 hours. That's a massive difference.
It's night and day from an operational perspective. A train out for 4 hours is an inconvenience. A train out for 3 days is a major headache, impacting schedules, availability, everything.
Does this relate to those common cause failures you mentioned?
It does to some extent. MVB's slightly higher susceptibility, that 2% beta factor versus Ethernet's 1%, is partly because its integrated nature and weaker diagnostics make it harder to isolate faults. A single issue might have wider, harder to pinpoint consequences.
So putting it all together for asset availability, Ethernet fails more often but is fixed way faster. MVB fails less often but takes ages to fix.
Exactly. And when you run the numbers for overall availability, the percentage of time the train is actually ready to be used, Ethernet comes out clearly ahead. We're talking figures like 99.965% availability for Ethernet versus 99.878% for MVB.
And in this calculation, the network does become a major factor.
A huge factor. The network's own maintainability contributes something like 30% to Ethernet's overall availability calculation, but a massive 62% for MVB, because those long repair times really drag its availability down.
So the choice of network technology suddenly becomes critical for keeping the fleet ready.
Absolutely critical for overall asset management and operational efficiency.
Okay, but these numbers, these conclusions, they're not absolute, right? They must depend on certain assumptions, especially around those repair times.
You're absolutely right. This is where engineers do sensitivity analysis. They ask, what if? What if things aren't quite like the baseline assumptions?
So what are the crucial sensitivities here?
Well, that super fast 4-hour repair time for Ethernet, let's call it MACMT1, for the common faults, is key. The analysis shows that if that average repair time creeps up, say, past 12 hours, then Ethernet's big advantage in maintainability starts to disappear. It might not be better than MVB anymore.
So keeping that Ethernet repair process efficient is vital.
Absolutely vital. It means having the right diagnostic tools, trained staff, and spare parts readily available. If you can't fix it quickly, you lose the main benefit.
What about improvements on the MVB side? Could better diagnostics help it catch up?
They looked at that too. Even if MVB dramatically improved its fault localization, say, going from a 10% chance of finding the fault quickly to a 60% chance, Ethernet still holds the advantage as long as its own quick repair time stays low, specifically under about 7 hours in that scenario.
So rapid repair on the Ethernet side is really powerful.
It really is. And even for the more complex, longer repairs, the MPC-MT2 Ethernet maintains its edge as long as the time for those complex MVB fixes stays above roughly 28 hours. Remember, the baseline assumption for MVB's longer fixes was around 80 hours.
This really highlights something crucial for design engineers, doesn't it? It's not just about preventing failures.
Not at all. It's equally, maybe even more importantly, about designing for maintainability. How quickly can you detect a failure? How accurately can you locate it? And how fast can you fix it and verify the fix? Those factors fundamentally drive the train's overall availability.
Okay, let's try and wrap this up. We've covered a lot of ground. What are the big takeaways?
I think there are two main ones. First, if your primary concern is service reliability, keeping the train running smoothly during its journey, then focus your efforts on the reliability of the end devices, the controllers, the displays, the sensors. The network type itself, MVB or Ethernet, doesn't make a huge difference there.
Right, network choice is less critical for the journey itself, but
But second, if you're looking at asset availability, the train's overall readiness to operate, including maintenance downtime, then Ethernet's superior diagnostics and much faster repair times, give it a significant advantage over MVB. This is true despite its components potentially failing a bit more often.
so the best tech isn't just about failing less.
Exactly. It's often about getting back up faster when you do fail. For complex systems like trains, efficiency in maintenance and diagnostics is just as important, if not more so, than the raw failure rate of components. That's a huge shift in perspective.
It really is. It makes you think about the trade-offs, doesn't it? In this drive for constant uptime, are we more willing to accept, say, more frequent failures if they can be fixed in minutes or hours, compared to rarer failures that might take days to resolve?
That's the core operational and design question. And it leads you to wonder, what's next? What kind of advances in, say, predictive diagnostics or even automated repair could change this equation again for railways in the future?
Definitely food for thought. Something to ponder next time you're on that smooth, reliable train journey.